Assalamualaikum and hi, I'm Johan Aliff, bin Ajhar from Group 4. So now we will present on the Reservoir Engineering Department. In this section, the depth for the term oil-water contact, which is WOC, and gas-oil contact, which is GOC, were defined. The values of GOC and WOC were obtained from the pressure gradient. The input values of depth datum, GOC and WOC for initialization were 1,494 meters, 1,468 meters and 1,506 meters respectively. And this is the map for the water saturation. First, water saturation. Second map is the ND poro. Third, permeability. Then RQI. And the last map is the SO. And now I will show you the data for the oil production and the recovery factor per well. Well planning was used to determine the optimum number of wells to acquire the maximum oil recovery. The amount of well decided was 6 production wells with drainage of 1,000 feet. And this table shows the production of oil at different well number, which is for the well 1. FOPT is 3.1 and the recovery factor is only 4%. For well 2, FOPT is 6.0 and the recovery factor only 7%. And the well 3, 9.4 and the recovery factor is 11%. Then for the number of well 4, FOPT is 11.7 and the recovery factor is 14. Then for the well 5, the FOPT is 14.2 and the recovery factor is 18%. Then for the well 6, FOPT is 16.9 and the recovery factor is 21%. And the last well is FOPT is 15.9 and recovery factor is 20%. So we choose 6 production well because the recovery factor is higher at the 6 well. And now this is our creaming curve. It shows the highest value at well 6. And now I will show you the data from our simulation. This is for the base case model. The base case is the production of oil with only the natural drive mechanism. There are 6 production wells with 15.185 mmSTB of production and 19% recovery. And this table shows the summary of the base case scenario, which is the drainage radius is 1,000 feet, flow rate control is 1,100 STB per day, and wellbore radius is 1.2 feet. Number of production well is 6 well. Number of injection well is 0 because this is the base case. Then the total oil recovered is 16.9 mmSTB, and for the recovery factor is 21.8%. And this is for the case 1, which is we put 2 water injection wells. The development of case 1 adds 2 water injection wells to the existing 6 production well. And this table shows the summary of the case 1, which is the drainage radius is 1,000 feet. The flow rate control is 1,100 STB per day. And still same for the production well, which is 6 well. And the number of injection well is 2. The total oil recovered is 20.4 mmSTB, and for the recovery factor is 26%. And this is for the case 2. The development of case 2 adds 2 gas injection well to the existing 6 production well. And this table shows the summary of case 2, which is the flow rate control is 1,100 STB per day. And the number of production well is 6 well, and the number of injection well, which is gas, is 2 wells. And for the total oil recovered is 17.4 mmSTB, but for the recovery factor is only on 23.2%. And for the last case, which is case 3, the development of case 3 adds 1 water injection well to the existing 6 production well. And the top table below shows the summary of the case 3, which is the flow rate control is still same, which is 1,100 STB per day. and for the production well is 6 well and number of injection well is 1 well. Total oil recovered is 17.9 mmSTB and the recovery factor is at 23.4%. And this is our production profile for all case. For the first graph is for the base case, second graph which is for the case 1, third graph is for case 2, and the last graph is case 3. And now we move to the total production profile for every case. Same as previous, first graph is for the base case, second graph is for the case 1, third graph is for case 2, and the last graph is for the case 3. And the conclusion, the classification of the reservoir is saturated reservoir and the oil produced are black oil with associated gas. For well planning, case 1 is chosen for its recovery factor of 26%, which is higher amongst all the other cases. And this table shows the overall summary of well planning. Thank you. Assalamualaikum and hi. And now we will present on the drilling engineering department. For the introduction, the drilling engineering and well completion for the proposed drilling program that can be safely executed by the drilling unit with a view to stability, operating limits, structural strength, and other important criteria during all anticipated combination of environmental and functional loading operation for Gelama Merah field are explained in Chapter 5. Gelama Merah 1 is a well in the Gelama field in Block SB 1812, which is part of the Sabah Basin, which is located off the coast of Sabah, Malaysia. The field is also close to a producing field known as Samarang Field, which is in the East Baram Delta region. Gelama Merah field has two wells, which are Gelama Merah 1 and ST1. The data used to design this drilling program was based on previous geology and geophysics practice, which included high-resolution geophysical site survey to determine the presence of shallow gas, near-surface faulting, slumping, unusual bottom features, and other potential shallow hazard before drilling operation begin. Aside from that, petrophysics interpret logging data that was utilized to validate and conclude the data from geology and geophysics so that the reservoir department may examine it further. And for the rig selection, Gelama Merah is located 43 km from Labuan and 130 km from Kota Kinabalu. The target location coordinate are 05, 33 and 49.98 degree north. Gelama Merah 1 was vertically drilled to maximum target depth and plugged, whereas Gelama Merah 2 was horizontally drilled to the maximum target depth and plugged. Another well, GMSC1, is then diverted to calculate the reservoir maximum drainage point. The criteria that were taken into account for rig selection in this drilling program are water depth, costing rig capacity and stability and availability. And this table shows the specification of the shortlist marine offshore drilling units that might be chosen for the drilling execution. Gelama Merah field has a water depth for 150 feet approximately, which is 42.8 meter. Considering all of the criteria required, three types of rigs seem to be viable with the execution condition, which are jackup rig, semi-submersible rig, and tender-assisted rig. However, among these three types of rig, jackup rig is chosen for the drilling program as it reasonably complies with all the required aspects. As for a long production projection, utilizing jackup rig is more cost-effective due to its lowest average daily cost estimation, which leads to lower operating costs for the operator. The other two types of rig have a higher average daily cost estimation, especially for semi-submersible rig, which might be overpriced for this field. Even though it has disadvantages such as not being able to accommodate the water depth and penetration into the seabed, and one of the legs might suddenly break down. Some improvement have been in current design of jackup rigs. Considering Malaysia monsoon weather environment, jackup rig adaptability were seen economical with a lower day rate, which makes jackup rig more preferable compared to the other two rigs based on Based on the water depth, Glamour Merah Field is considered as shallow water. Therefore, water depth shall not be an issue as jackup rig can be operated up to about 400 feet. The data of the well location has been provided by the reservoir department. The well location was determined after studying the flow assurance of the reservoir characteristic of Glamour Merah Field. Three cases were proposed to achieve optimal recovery. Comparison has been made between the two cases and case 1 has been chosen as it shows a higher recovery factor of oil production. And then this is the bubble map of the Glamour Merah field that include 6 production well and 2 injection wells. As you can be seen in this figure, the top view of the location of the well shows that the wells were positioned accordingly in the target production areas. It clearly shows the location of the production wells and injection wells in case 1. Water injection was employed to push the oil towards the production well. This is because the reservoir itself is experiencing gas and solution gas drive. Thus, if gas injection is used, it will not affect the change of pressure in the reservoir. This will only increase the amount of gas in the reservoir and need to be overcome as no gas production was done for this field.
In the casing and cementing, we need to calculate the casing setting depth. Based on the MDT data obtained from the GM1 exploration well, the pressure profile was plotted. From this pressure profile, it actually indicates the formation pressure, pore pressure, and overwhelming pressure that exerted in the Glamour Merah field area. Therefore, to determine the fracture gradient of the pressure profile, we will use the U-turn method by using the formula as you can see here. From here, we can see that the table shown is actually the depth and pressure at the allocated casing that has been given. From the figure in the next page, it actually shows the casing configurations of the casing setting of the well after using the pressure profile to set the casings. The figure below shows the casing setting depth of well using the pressure profile. As we can see here, the conductor casing is set at a depth of 350 meter. For the surface casing, it is set at the depth of 580 meter. The intermediate casing is set at a depth of 900 meter. And the production casing is set at a depth of 1600 meter. For the casing seat selection, it is essential to choose a casing seat that can withstand the maximum pressure to which the wellbore will be subjected during drilling of the next hole section. There are two methods to select the casing seat. The first one is based on the mud weight, and the second one is based on the gas influx pressure. For this development plan, the method of gas influx pressure was chosen as the casing seat selection method. For the well stick chart, as you can see here, the figure shows the well stick chart for all the casing setting depths. The locations for all the wells are shown. For the casing design, it was done based on the Petronas PPGOA Volume 8 PCSP Drilling Manual, Well Design Manual, WDM. The design factors used were taken from PCSB and shown in the table below. For the collapse design factor, we used the 1.0 safety factor. For the brace design factor, we used the 1.1 safety factor. And for the tension design factor, we used the 1.3 safety factor. Then, the collapse load, burst load, and tension load of the casing were calculated for each type of casing based on the selected safety factors. The table shows the casing weight and grade that's suitable to be installed. So, for conductor casing, we use the grade for J55. For the surface casing, we use the grade for L80. For the intermediate casing, we use the grade for L80 as well. Same goes with the production casing, we use the grade for L80. For the cement selection, cementing is one of the most significant processes in a drilling operation. Among all the types of cements available in the industry, we use the Class G cement because it has the most suitable and recommended type of cement. Why? Some of the benefits of Class G cement include the high pressure resistant, high temperature resistant, can be modified by using additive to suit any application, has a consistent quality for slurry design portability. Therefore, Type G cement was chosen for cementing job in Amirah field. The table below shows the purpose of cement design, which is for the type of casing, and we can see the top of cement and the value for the lid and tail for the cement design.
Present about the drilling fluid selection. Drilling fluid is referred to drilling mud or fluid that are most often circulated down the drill string out the bit and back up the annulus to the surface. There are several principal functions of drilling fluid, which is to control subsurface pressure, maintaining well control, remove the cutting from beneath the bit and circulate them to the surface, maintain wellbore stability, mechanically and chemically transmit hydraulic energy to the drill bit and downhole tools, cool and lubricate the drill string and bit. Several factors need to be considered, such as well design, formation pressure, mud weight, design range, and fracture gradient of the formation. This is the mud window for the Amirah 1. The blue line is the formation pressure, and the kick margin is always 0.5 ppg overbalance more from the formation pressure, and drip margin is always 0.5 less from the fracture gradient. And this is the accumulated mud weight from the MDT data, and this is the allowable range for mud weight for the Amirah 1. This is summary of drilling fluid selection from each casing. Depth 340 meter conductor, seawater, weight is piling. Depth 580 depth surface, which we use the type of fluid is water based mud, KCl, potassium chloride, and PHPA, partial hydrolyzed polyacrylamide. For depth 870 casing intermediate, we use the same water-based mud, KCl and PHPA, WBM also for the production water-based mud, but different mud weight. For surface is 9.20, for intermediate 9.35, and for the production is 10.20. Another factor that we consider to use the water-based mud because it is low cost, eco-environmentally friendly, and availability. The addition of the additive, which is partial PHPA, partial hydrolyzed polyacrylamide, and potassium chloride, is to stabilize the shale in the reservoir formation and help to overcome the swelling of the clay and shale formation, which can cause the pipe stuck during the drilling operation. Next is drilling waste management. Start with the source reduction. We use the water-based mud instead using the oil-based mud or synthetic-based mud. And recycling, re-injection. From the drilling waste, we re-inject to the well for abandonment or for maintain the pressure of the reservoir. And the last but not least is the treatment. We're treating the drilling waste mud before we dispose it, because based on the Malaysia regulation and guideline, water-based mud is allowed to disposal to the sea, but we need to wash it properly before we dispose dispose it to the sea. This is the potential hazard for drilling. First is loss circulation that comes from the uncontrolled flow of the whole mud into the formation, high permeability of the formation. The mitigation plan is use the optimum value of mud weight, always check and update the formation pressure. Second, borehole instability, mud weight density too low, natural fracture or faulted formation. We must use the proper mud weight selection and maintenance. Drill pipe failure, twist off, parting, burst or collapse. Another cause is the unconsolidated sand, and the mitigation plan is proper handling and inspection of the drilling string on a routine basis, ensuring the availability of the detailed geological and seismic information. Last but not least is the shallow gas. Unexpected gas bearing zone encountered before the rig can set the BOP. Drill with caution. The mitigation plan is drill with caution while monitoring for any abnormal drilling parameter recorded. Hello, Assalamualaikum warahmatullahi wabarakatuh. My name is Mohammad Aiman bin Amer from Group 4, Gyrffindor. I would like to present about production technology for our FDP. First, there are several objectives of production technology. First, to provide safe, cost-effective and the most efficient strategy on the production method, well completion technique, artificial lift method, sand and potential problem control technique based on the well performance analysis. Second, maintain well integrity during the production life while maximizing the recovery. Third is to identify potential production problem and its control measures. Next, production technology plan and strategy. Well performance. Production optimization using nodal analysis method by doing PVT and IPR matching from the exploration wells. Some of the parameters that will be tested are optimum tubing size. Second is water cut percentage on the production. Third is gas oil ratio effect on production. Next is well completion design and artificial lift, sand production prediction and control. Based on review core data, potential production problem, review historical data, and based on the data interpretation. And last but not least is design model. Next, well deliverability and performance analysis to evaluate the performance or behavior of petroleum fluid flowing in Amer field by using the pipe scene. In order to evaluate the performance or behavior of petroleum fluid, the relationship between inflow performance relation and tubing performance relation (TPR) of the well play the important role. The base case model is developed by determining the intersection of two performance curve, which is IPR and TPR, to define the operating point of flow rate and pressure. The absolute open flow AOF is around 5,800 stock ton barrel per day. The production index of Amer well deliverability is calculated using equation below, and J obtained is 3.16 STB per D per PSIA. Next is sensitivity analysis on optimum tubing size selection. Selection of optimum tubing size using sensitivity analysis is important for efficient operation. For present and future performance of GM well is evaluated accordingly. There are several important parameters that need to be accounted. First is tubing size, second reservoir pressure depletion, third well heat pressure, fourth water cut, and fifth is gas oil ratio. We start the nodal analysis with the tubing size. As we can see, we put the range of the tubing size in millimeter from 2.4 until 5.0. The tubing the tubing able to operate with the trend tubing size. The larger the tubing size, the higher the flow rate. Next is a reservoir pressure depletion. We put the future IPR for the tubing size to see the tubing size able to operate for the future reservoir pressure. We put the range as 2200 until the 1100. As we see at the nodal analysis, the VLP for the all the tubing size do not intercept with the IPR for the 1100. So we can conclude that the tubing size range from 2.4 until 5.0 are able to operate until 1600 uh, reservoir pressure only in the future. This is the sensitivities analysis for the wellhead pressure. Same trend with the previous one. The larger the tubing size, the higher the production rate. But for the water cut is different. Water cut is different because only three tubing size that able to operate at water cut 60%, which is a 2.4 2.4 2.992 and 3.548 inch only able to operate at 60% of water cut. And we choose the tubing size for this production is 3.548 because uh, this is the only one the tubing size able to operate when the water cut is 60%. Next is the material selection is one of the important step in completion longevity and the design life of the completion in oil and gas. It is compatible with the production profile of the well for the Gelama Merah. This step is based on the content of hydrogen sulfide and carbon dioxide because both of them can affect the tubing material. This is the calculation that we made to calculate the partial pressure for CO2 and H2S. The CO2 content percentage is 2.96 based on the reservoir report, and CO2 is and we get the CO2 partial pressure is 58.27. H2S is 0 and we get the H2S partial pressure is 0. So based on the Sumimoto chart, we can say the most suitable material for Gelama Merah is SM13CR-80 for the material selection.
Assalamualaikum and a very good day. My name is Amirah Najwa Binti Hamid and I am from Group 4, Gryffindor, and I would like to present about the Facilities Engineering Department for our field development plan. For the Facilities Engineering, the Gelama Merah field is located inside the Labuan Pasir Syncline, about 43 kilometers from Labuan and 130 kilometers from Kota Kinabalu. Since the water depth is roughly 50 meters, a jackup rig will be utilized to drill the Gelama Merah field. So for this Facilities Engineering, we have been planning and designing suitable facilities for the oil and gas production, and also we need to decide the optimum platform and transportation in the facilities. In oil and gas properties, we have to calculate the GPM value. GPM is used to calculate the amount of natural gas liquid in natural gas stream, which is defined as the number of gallons of hydrocarbons contained in 1000 cubic feet of gas. So this table shows the summary of GPM calculations, and the total value for GPM is 2.2106. The total GPM shown in the table is 2.2106 GPM. This shows that the gas is lean gas because lean gas has a flow rate of less than 2.5 GPM. So as a result, one of the surface processing equipment, namely the NGL recovery process, is not required for design in this project, as the flow rate for the gas is lean gas compared to moderately rich gas, which has flow rate 2.5 to 5 GPM, or a very rich gas which has rate of more than 5 GPM. We also need to determine the water content in the oil and gas properties. By determining the water content in natural gas is very critical for maintaining the pipeline quality control and also reducing the possibility of corrosion, safety issues, and infrastructure damage that can result from high water content levels. So for this plan, we have two types of approaches for determining the water content. The first one is by utilizing an equation. The second one is by using the charts. So this is the first method for the determination of water content. The first thing that we have to do is that we calculate the mole fraction of water, and then from the mole fraction of water that has been calculated, we can know the total pressure. Then we can calculate the amount of water content, which is we will get 251.39 pound H2O per scuff of gas. For the second method to determine the water content, this is the table that we need to calculate by listing the component for the oil and gas properties, and we can know the total from the mole fraction times with the molar mass. And then from the value of gas gravity, we calculated by using the formula below. Then we can know the water content from the graph, and the gravity correction, salinity correction, and also the water content. And we will get 282.24 pound H2O per scuff gas, which is the second method is actually preferable compared to the first method because the second method is more accurate. For oil and gas processing, this is the overall PFT for our facilities. So we have been decided to have 6 production wells. So as we can see here, they have 6 production wells and also other systems in the overall PFT such as water injection and water treatment system, gas treatment system, and also the flash system. So this is the PFT for gas treatment system, which we have been choose to use the gas dehydration system to remove the water from the gas flow. This is the PFT for the water treatment and water injection system. And this is the PFT for the flash system in the facilities. For the wellhead is the component at the surface of oil and gas that provides the structural and pressure containing interface for the drilling and production equipment. While drilling the oil well, surface pressure control is provided by a blowout preventer which is called as BOP, and the wellhead's mechanism is that the air instrument will drive the wellhead panel. Individual well fluids will then flow through the Xmas tree before being routed to the production manifold. The production manifold is used to arrange the piping from wellhead provided in the Central Processing Plant (CPP). These manifolds help to allow setup of production which is called as well sets. Oil and gas manifolds helps to divert the flow of oil and gas from separator to other equipment. For separator design, separator is used to separate the flow into the reservoir fractions, and it can be split into few configurations. So for this plan, we have been choosing the horizontal separator. This is because horizontal separator has smaller diameter and has low cost. It also has large gas liquid interface, which helps the gas bubbles to come out of solution as the liquid approaches equilibrium easier. It also offers liquid capacity, which has a greater capacity and the best suited for liquid-liquid separation. For compressor can increase the pressure of a gas by reducing its volume, and it can be used whenever it is necessary to flow gas from a lower pressure to a higher pressure system. So for this plan, we have been choosing the rotary compressor because it has the maximum delivery pressure at 10 bar only, and the maximum free air discharge rate is as high as 3000 meter cube per minute. Rotary compressor also can easy to be installed and to be maintained. The supply of air for rotary compressor also is continuous. For pump also can increase the pressure of fluid line. For this development plan, we have been choosing the centrifugal pump compared to reciprocating pump because centrifugal pump has low and average efficiency, and it also has low cost for maintenance. And the flow rate for centrifugal pump is high and very excellent for the oil and gas processing. For the platform types, in this project, we have been proposed three different options to decide on the platform, which are semi-submersible platform, jacket platform, and gravity-based platform. So we have been decided to use the jacket platform as it gives more advantages compared to others. Jacket platform is suitable for depth up to 500 meter, which is appropriate for Amirah field. It is designed for a long-term use, and it also can support large deck loads, which consist of two types of decks, which are conventional decks and modular decks. The cost for building the jacket platform is about 50,000 to 60,000 USD, which is cheaper compared to other platforms. For the oil and gas transportation, for this project, there are two options for the transportation for the delivery method. Option 1 is pipeline to LCOT or LGAST. Option 2 is by tanker with FPSO. So the facility department has decided to use the pipelines. This is because the distance for pipeline from CPP is 40 km, which is suitable for our field. The cost is also cheaper compared by using the tanker, and the capacity is depend on the size of the pipe, and it also has low energy consumption.
Assalamualaikum warahmatullahi wabarakatuh. So for this section, I would like to present to you for the economic department by Group 4. The objective of this economic department is first to generate the reliable economic assumptions according to the current economic situations, and second is to summarize the technical input in order to calculate the cost and revenue for agglomerates. To do the economic assumptions, we will use the petroleum fiscal terms. This term has been applied since 1997, and it is known as National Production Sharing Contract, which is PSC. PSC has been conducted by Petronas, and most of these PSC are based on the revenue over cost. The PSC is a set of laws that has been used in which the government will get the economical benefits from the oil and gas explorations and production activities in this country. The fiscal terms that has been applied since 1997. For the royalty will be 10% of revenue, and petroleum income tax will be 38% of taxable income. For the export duty will be 10% of profit, and Petronas Regalis participations will be 20%. The contract durations will be 29 years, and the production period will be 20 years. Gas price and oil price, we would like to use the US EIA oil and gas price forecast. This is the EIA oil and gas price forecast in between year 2021 and 2038. In this table, for oil price, it would like to be 148.52 USD per STB, and for the gas price, it would like to $2.36 USD per MMBTU. This oil price is referred to the year 2021, and the production period will be 15 years and development period will be 3 years. For the escalation rate, the actual oil price will be 3% of escalation rate and base oil price will be 6%. For the capex and opex, escalation rate will be 5%. Next, for this table, it refers to the productions profile in Reservoir Engineering department. As you can see, our group will choose case 1 as the best choices for the explorations and productions activities because it has the highest recovery factor for oil, which is 26.0%. This case will conduct 6 production wells with 2 water injection wells. This is the total capex for the case 1, which is the total of the capex will be 339.24 USD. Next, for the OPEX calculations for Gula Amirah, it would like to be 1.534 USD. For URC, UDC, UOC, and UTC for the Gula Amirah. As we calculated, the UTC for Gula Amirah would be 1.602 USD per square feet. That's all from us. Thank you.